Konnichiwa! We are on our last lesson of curve sketching, and it's just going to be more examples. These examples take a long time to do because there are so many calculations we have to do with each one, and that's why we're spending so much time on it. So let's take a look at another example right now. Examine the function f of x equals x times e to the x for the following properties and use that information to sketch a graph. Let's look at these one at a time. We'll start with the domain. The domain here is all real numbers because there is nothing that we can't plug in. No radicals that we have to worry about or things in the denominator or logarithms. X and e to the x are both defined on all real numbers, and so is their product. For intercepts, the y-intercept, when we plug in 0 for x, 0 times e to the 0, well, 0 times anything is 0. So we're going to have an intercept at 0, 0. That's both a y-intercept and an x-intercept. For the x-intercept, we need to know when x times e to the x equals 0. Well, certainly x equals 0 gives us one x-intercept, but e to the x is never equal to 0. That factor is never going to equal 0, so there are no more intercepts. It's just going to be 0, 0. For symmetry, there is no symmetry here. E to the x is not a function that is symmetric, and multiplying that by x doesn't change it. There is no symmetry here. As far as asymptotes go, if this x wasn't here, and it was just f of x equals e to the x, we know that there would be a horizontal asymptote at y equals 0. The x-axis would give us a horizontal asymptote, specifically on the left-hand side. As x goes towards negative infinity, e to the x approaches 0. But the problem is that we've got this x here, which makes things more complicated. At this point, what we can do is we can look at values of x that are getting larger in the negative direction. So we can look at x equals negative 100, x equals negative 1,000, x equals negative 10,000, etc. We could make a table of values. If we do that, you can plug those into your calculator. You will see that this is getting closer and closer to 0. So we do end up having the limit of this function as x approaches negative infinity equaling 0. So that is going to give us a horizontal asymptote on the left-hand side. I will leave it up to you to make that table of values. You can very easily plug these into a calculator and look at those values, but they are getting closer and closer to 0 as x moves further and further in the negative direction. So that is going to give us an asymptote. For the intervals of increase or decrease, we're going to need the derivative. So f prime of x, we're going to have to use the product rule. We've got the derivative of the first factor, derivative of x is 1, times e to the x, plus the first factor x times the derivative of the second. The derivative of e to the x is just e to the x. So if we factor out an e to the x, that's e to the x times x plus 1, or 1 plus x. Doesn't matter either way. We can make a sign chart here, then. We need our critical numbers. This is never undefined. If we want to know when it equals 0, remember e to the x never equals 0, but x plus 1 equals 0, specifically when x is negative 1. So our only critical number is negative 1. So if we look at our factors, e to the x is always positive. X plus 1 is going to be negative when x is less than negative 1 and positive otherwise. So our derivative is going to be negative and then positive, meaning our function is decreasing and then increasing. So we have a local minimum at negative 1. And if we plug negative 1 into our function, we've got negative 1 times e to the negative 1. That is the same as negative 1 over e. So that gives us a local minimum value. And then we can take the second derivative to figure out concavity. The second derivative is the derivative of the first derivative. The first derivative is e to the x plus x e to the x. Now, here's an interesting thing. If we want to differentiate e to the x, that is just e to the x. So that part is easy. And then the second term that we need to differentiate, if we want to differentiate x e to the x, here's the funny thing, we've already done that because the original function was x e to the x, and we've already calculated that derivative. It is e to the x times x plus 1. So if we want to differentiate that again here, it's just going to be e to the x times x plus 1. And so if we want to combine these, this is going to end up being e to the x times x plus 1 plus 1, or x plus 2. So we end up with e to the x times x plus 2. Now, the only critical number here is going to come from when x plus 2 equals 0, and that's going to be x equals negative 2. So we've got one critical number here. And so we can set up our sign chart. We've got negative 2. E to the x, again, is always positive. X plus 2 is going to be negative when x is less than negative 2, and then positive. So our second derivative is going to be negative and then positive. So that's going to be concave downward up until negative 2, and then concave upward after that. So that is good to go. I think we've got all the information we need, and we can start plotting these points and graphing things out. I'm going to switch to the graph paper that I actually use when I teach in person, because I think it's good to get a little bit of practice here. And let's see, what information do we have? We know we have an intercept at 0, 0, both an x-intercept and a y-intercept. We know that we have an asymptote at y equals 0, specifically in the left-hand direction. We saw that when x approached negative infinity, our function was getting closer and closer to 0. So we've got a horizontal asymptote on the left-hand side. We also had a point that was a minimum value. If we plug in negative 1 over e to a calculator, that's going to be approximately negative 0.37. So that's going to be at negative 1 comma negative 0.37. It's going to be right around there. And what is happening in each of these intervals? We know that the function is decreasing to the left of negative 1, and then it's going to be increasing to the right. And we've got concave down to the left of negative 2. So we've actually got one more point we need to put on. We need a point at negative 2, because that is where our inflection point is going to be. So that's going to be at negative 2, comma, and then that's going to be negative 2 over e squared. And if we use a calculator to approximate that, negative 2 and then approximately negative 0.27. So that's going to be even closer to the x-axis. And we are concave downward to the left of that, but then concave upward to the right of that. So let's see what's going on. To the right of our minimum, we are increasing and concave up. So that's going to look something like this. Though we don't know exactly how steep it's going to be. We might want to come up with another point if we want to be more accurate over there. And then on the left-hand side, everything is happening close to the x-axis. In here, we're going to be decreasing, and we're going to be concave up for a little bit, but then on the left, we're going to be concave down and asymptotically approaching the x-axis. So it's going to look something like this. I mean, at this point, we're getting so close in that it's hard to draw anything nice. I'm actually going to erase a little bit of this here because I do want to show the concavity if I can manage it, because it is concave down up until that point. So that is, I guess, a little bit more. If we were to zoom in, we would have concavity downward and then concavity upward like that. So this is kind of, if we were to zoom in and have a little bit more space to draw, that's a little bit more what's happening here. But it is what it is. This is the axes that we have, and that is a sketch of what this graph is going to look like.